Hello, my name is Dr. Evan James Gowan, but you can call me Evan. Welcome to the Raised Beaches podcast. This podcast will discuss topics related to paleoclimate, earth science, and global change. This is episode 1, so first, I'll give an overview as to the format of this podcast. So the introductory part of the podcast, I'll discuss some topics that are relevant to whatever I've been looking at over the past few days before I record the podcast. The second part, I'll give a deep dive into some concept related to paleoclimate and global change. After that, I'll give a more casual discussion about the references that I used for that specific topic. Finally, I'll give an overview of some recent papers that I found interesting. Now first, you're probably wondering who is Evan Gowan? Well, here's a bit of background into how I got to be a paleoclimate scientist. I did my undergraduate degree in the University of Manitoba from 2000 to 2005. Manitoba is in central Canada, if you don't know where that is. In that degree, I studied geophysics. Didn't really have much to do with climate at that point. I studied, for my honors thesis, a geophysical technique called magnetotellurics. This is a geophysical technique that measures natural electrical and magnetic fields to determine the properties at tens of kilometers below the surface. After that, I decided to do a master's degree. I went to the University of Victoria in British Columbia. It was there that I began to get interested in paleoclimate topics. Even though I was at the University of Victoria, I was mostly located at the Geological Survey of Canada. For my master's thesis topic, I was initially mostly interested in the properties of the mantle, which is several tens of kilometers below the surface. However, to investigate the mantle, we used a technique called glacial isostatic adjustment. I will talk about that in one of my main topics in a future episode. So with glacial isostatic adjustment, basically what that is you load ice on the surface during a glacial period, and that deforms the Earth, and that will also affect sea level. So my master's topic, half of it was about determining the sea level history of Victoria, and the other half was deducing the size of the ice sheet through the modeling the glacial isostatic adjustment response of the Earth. After that, I went into the private sector, specifically the mining industry. I wanted to make some money, and also I didn't want to go straight into a PhD. Anyway, that turned out to be a little bit of a disaster because while I was working in the mining industry, the 2008 financial crisis happened, and eventually all the jobs sort of dried up. After that, my boss recommended that I should pursue a PhD because he didn't think things would improve anytime soon, and he was kind of right. And anyway, having lived in Canada all my life, I decided it was best to go overseas somewhere to pursue my PhD. And so I went to Australia, the Australian National University. The Australian National University is a very famous university in the history of earth sciences because it was one of the first major institutes that accepted the theory of plate tectonics. It also has a long history of climate science, and I wanted to continue my interest in ice sheets and glacial isostatic adjustment, and that was a good fit for me. As it turned out, my supervisors decided that because I was from Canada, I should pursue a project related to the ice sheet history in North America. was right in my backyard where I grew up, all of the data that I used. But I was in Australia, so that was kind of funny in some ways. So anyway, I did my PhD between 2010 and 2014. And after that, as is pretty common for people who want to pursue an academic career, you start to do a postdoc. For that, I went to Stockholm University, and that was a bit of a change of pace. So instead of looking at glacial isostatic adjustment, I moved into modeling ice sheets. And my postdoc in Stockholm University in Sweden was a bit short. It was about a year and a half, but I learned a lot about ice sheet modeling. So how does an ice sheet flow? How does it respond to climate? So that was a very important introduction for some of the stuff I did later on. In 2016, I got a postdoctoral position at the Alfred Wegener Institute in Germany. So you may have heard of Alfred Wegener because he discovered the concept of continental drift when he found out that South America and Africa kind of fit together in a perfect, like a puzzle piece, basically. However, Alfred Wegener was actually a very famous polar scientist, and in fact, he died while he was on top of the Greenland ice sheet. So this is a pretty exciting place to be if you're interested in ice sheets. So I spent 5 years in the Alfred Wegener Institute in Germany, and the first couple of years I was primarily focused on doing more ice sheet modeling, and in particular I was interested in how changes to the conditions at the ice ground interface affect the sliding and history of the ice sheet. And after that, I worked on a project that was more related to glacial isostatic adjustment, sea level change. And in that project, I ended up going to Argentina, and that was a lot of fun. And I learned so much. I also got started in compiling sea level constraints of the past, and that has culminated in me making a database, an online database called the Global Archive of Sea Level Indicators and Proxies, or GAPSLIP. And that has been something that I've been working on a lot lately. So after 5 years in Germany, I ended up moving to Japan in 2021, and I took a 2-year postdoc at Kumamoto University. Now, most people probably don't know where Kumamoto is, and part of the reason I moved here was for family reasons. But of course, I love Japan, and it's great that I'm able to live here. And in this 2-year postdoc, I was working with Dr. Tomita, who's interested in the rainy season, which happens in June usually. I say that now as I'm recording this in mid-June, and it's supposed to be the rainy season here, and it is very dry and hot. But anyway, our project was mainly to look at what the changes in sea level during the last glacial maximum about 20,000 years ago, and how that impacted the rainfall patterns in Eastern Asia and Japan. That's pretty interesting. Still not quite done. I've got paper revisions still to write up here, so wish me luck on that. That finished up about 1 year ago, and since then I've been still associated with Kumamoto University. Dr. Tomita has been very generous and given me some support to maintain my affiliation there, and I'm really appreciative of that, of course. And but yeah, the past year I've been doing lots of traveling and lots of pondering about what I should do for the future, because after almost 10 years of doing postdocs, I feel like the next step needs to happen. And of course, getting a permanent position in academia in 2024 is very difficult. There's not a lot of positions. And as a result, I experimented with a few different things. I pondered going into the private sector, and I thought about, well, what's hot now, of course, is the AI and machine learning, and I even bought some textbooks on that and pondered, should I do that? And I decided, by the time I teach myself how to do machine learning and AI techniques, that this fad, I'm calling this AI thing a fad, might be over. So yeah, it would take some time, and I don't know if I would enjoy all of the programming. I can do programming, but it's not my favorite thing to do. So I also considered, of course, I continue to apply for things, but there's not a whole lot available right now. I decided instead, why not try striking out on my own and start a podcast? And, I've been thinking about doing a podcast for years, and the reason I never did it is because I assumed it would be a very time-consuming thing, and that's very true. And but yeah, I'm unemployed, so I have all the time to be able to do that. And so yeah, I decided, let's do this. I got the fancy microphone and the lights, and I'm recording. So after I decided to do that, I saw this really interesting video by noted physics YouTuber Sabine Hossenfelder, where she basically had a lament about why she stopped being an academic and started to be a YouTuber. And having been through the German system, I very much sympathized with what she went through. And yeah, and she said, unless you are working on the hot topics, it's really hard to get funded. And that's so true. I submitted funding to the Japanese funding agency to continue doing my research, and guess what? It didn't work out. I published a paper that is probably one of the most cited earth science papers published this decade, and even then it was not possible to get funding. And of course, right now everything is all AI and machine learning, so your chances of getting funding are probably higher if you do something like that. But for what I want to do, that I think it's the wrong approach. So that's just how I feel, and nothing's going to change that. And anyway, with a podcast, I get to talk about what I want to do, and I hope that everybody will enjoy this, and I'm very excited. Of course, before I move on, I'd like to give some thank yous. And first off, I'd like to thank Aruj, who made my great retro 16-bit logo. It's perfect for what I wanted to do. It shows me holding a GPS unit, measuring a raised beach. And I'd like to thank Sean, who created the nice 16-bit style theme song. And of course, I'm a big fan of the Super Nintendo, as you might imagine if you know me. And yeah, I absolutely am very thankful that they were able to do such a great job. And I think the retro theme really suits the Raised Beaches podcast, which is about paleoclimate. course, I'd also like to thank that blasted Salami. He's a Tekken YouTuber and creates great guides for Tekken, and he's given me, so Arya, his name is, he's given me lots of advice about how to get this set up, including the equipment that I need, and I'm very happy he's been able to help me out. And of course, I'd like to thank Dr. Tomita at Kumamoto University, and he's been supporting me the past few years, and I definitely would not be able to get started on this without his support. So anyway, the next thing I'd like to talk about is the Japan Geoscience Union conference, which I went to in May 26th to May 31st. And I'm recording this on June 15th. And so it's been a couple of weeks since it's been over. And by the time you listen to this, it'll probably be a bit later than that. But I hope that you enjoy listening to some of the highlights that I thought were definitely worth mentioning here. So for anybody who doesn't know about scientific conferences, like, of course, you get to learn about the latest science. And in Japan, there's lots of great earth science going on. The Japan Geoscience Union conference is more of a local conference. So a lot of the sessions are in Japanese. And of course, I do know some Japanese, but for me, the main benefit is to learn some of the Japanese jargon of earth science, and that's always fun. But yeah, one of the main reasons you go to a conference is to network and to meet new people, and you want to sort of advertise what you're doing. Like, if nobody knows who you are, they're unlikely to read your papers. That's just the reality. It doesn't matter how good your stuff is. If nobody knows who you are, they probably will not notice your research. So I gave a presentation on my my sea level database called GAPSLIP, or the Global Archive of Sea Level Indicators and Proxies. And if you look at this channel, I made a video of that if you want to watch more of that. The highlights, perhaps the biggest highlight in terms of presentation that I saw was a presentation by Takuya Itaki. And in that presentation, he was showing off this machine learning techniques for detecting radiolarians in thin section slides. So a radiolarian is a type of plankton that you find in the ocean, and this settles down onto the ocean floor. And counting these by a human, like a person, it's very tedious. So basically what he's done is created a machine learning technique to identify these radiolarians using a computer. And it's not perfect, but it's got a 90% success rate. So basically it makes it possible to do very high resolution counts in a sediment core. And that's very exciting, because he's like, the machine learning tool it takes about 48 hours to do something that would take a person like 2 years to do. So it's very exciting. I'm sure this can be used for a lot of different proxies. There was a Pacific Islands Holocene session, and for me, the highlights were the tsunami talks. So on the Pacific Islands, they were looking at what past tsunamis, like rocks that had been washed up due to the tsunamis. And one of the alarming things was that there were these this tsunami that happened in the 15th century, and this was caused by a subduction zone called the Tonga Trench, and obviously, if that ruptures again, it'll be very devastating for the Pacific Islands regions and probably places like Australia and New Zealand. So definitely something people need to be aware of. In the ice core session, there was a presentation by Ikumi Oyabu, and her presentation was to refine the age of the last interglacial in the Dome Fuji ice core. And what they found was the last interglacial, the peak warming of it happened about 128 to 132,000 years ago. And they also estimated what the change in temperature relative to present was. And it was a bit lower than the previous estimates. And it was actually a bit closer to what is estimated from climate models, which is very encouraging if you want to trust the climate models. Stefan Hetzinger presented a new proxy record based on coralline algae that forms on rocks in Greenland. And by measuring the magnesium and calcium ratio of these coralline algae, he can find out the water temperature. And by measuring the barium calcium ratio, you can detect the amount of runoff coming from the Greenland ice sheet. And so basically every year there's a new layer of this coralline algae that forms on the rocks. And this is important because we only have records of the Greenland ice sheet melt going back, a couple of decades, or maybe 3 decades or so. So these records can go back a bit further back in time. So that's really nice. Another study that was presented was by Tsung-Mi Hu, and he reported on a speleothem, which is a stalactite. It's a carbonate rock that forms in caves. And this was a speleothem from northern Italy, and it provided a high-resolution record from Marine Isotope Stage 11. And this period is interesting because it happened about 400 to 420,000 years ago, and it's assumed that this is the warmest period in the past 3 million years or so, and therefore it's sort of a proxy, or it sort of will work as a way to understand what would happen in a warmer world. And for me, the big point of that presentation was that the interglacial conditions, so the warm conditions that are similar to present, were reached by 425,000 years ago, which is earlier than what has been assumed before based on marine records. So I think that it's going to be a very important study, at least for some of the stuff that I work on. Another poster presentation was by an honors student named Catherine Melissa Smith, and I looked up all the abstracts for paleoclimate sessions, and of course this one popped up because it had my name on it in the abstract. So what she was looking at was some corals from Kikaijima, which is an island in southern Japan, which is rapidly uplifting. And this island, I'll talk about Kikaijima in a future episode because I plan to go there in the next month or so. And she got some samples from this period known as Marine Isotope Stage 3, which is between 27 and 57,000 years ago. And these coral samples she tried to find a date from them. And based on what we know about the living depth that the corals live in below sea level, you can sort of deduce what the past sea level was. And Of course, her supervisor is Dr. Yusuke Yokoyama, and we don't always agree on the interpretation of some of these records. So we're kind of joking that the student, she was going to defend her thesis just a couple of days after the presentation, that she had already done her defense by talking to me. But anyway, I really hope she did well. Another poster that I saw was interesting was by Yijing Zhang, and he was investigating a sediment core that was taken from the Kanto Plain, which is fairly close to Tokyo. And anyway, this is a very long sediment record stretching back the past 400,000 years, and the Kanto Plain is slowly uplifting due to tectonics, but it's still fairly slow. And what was interesting to me, of course, as a sea level researcher, is that they found several fluctuations of sea level which are related to the glacial cycles. And of course, I will definitely be looking into that a bit more for my own interest. Another presentation on sea level change was by Satoshi Sasaki. The Japanese government has a research base in Antarctica called Showa Station, and Sasaki-san was investigating what is known as an isolation basin. So basically, the land in that area is slowly uplifting because of the unloading after the ice melted away. And this will be something I discuss more in a few minutes. So this lake is called Lake Funazoko, and basically, because the land is uplifting, they wanted to know, was it connected to the ocean at some point? And they found out by investigating the sediments from the lake that this lake was connected to the ocean at about 2,000 years ago and prior to that. So that's interesting information if you want to deduce the size of the ice sheets in the past. So anyway, I had a really good time at the Japan Geoscience Union conference, and I met all my great colleagues and met some new colleagues that maybe I'll work with in the future. And I can't wait for the next conference. I always have a good time. And anyway, next I will be on to the main topic, which will be what are raised beaches? This is episode 1 of the Raised Beaches podcast. So in today's deep dive, I thought it would be best to explain what is a raised beach. Currently, it's the middle of the summer in the northern hemisphere, and if you're like me, you want to hit the beach. Of course, what is a beach? Of course, you really think about it. It's something that's at the place where the ocean meets the land. And yes, a beach, by the best geological definition, is an unconsolidated sediment that is deposited by the action of waves and currents. Of course, when I'm talking in this episode about beaches, I'm talking about beaches at the ocean. I'm not talking about lakes. Of course, beaches can form at the coasts of lakes, and I will get into that in another episode, I'm sure. So the most strict definition of a beach, though, is where is the highest elevation reached by storm waves and the low tide mark. Because of this relationship of a beach to the position of sea level, it is often used as an indicator of past sea level position. So this is a very famous thing, and I will talk about this more later in this deep dive. raised beaches were first discussed in the early 1800s, and it was one of the first pieces of evidence to show that the Earth's surface was not static and it was not unchanging. So the early reports on raised beaches influenced the then nascent scientific discipline of geology. But, we know about beaches that are at the coast now. What is a raised beach? So raised beach is a landform that is above present day sea level, and it shows that in the past, in a relative sense, sea level position was higher than present. And that's an important thing to note, is it's what is known as relative sea level. So sea level is actually not something that is the same in time and space. And I'll discuss that more in episode 2. But the important thing to know is that in a relative sense, a raised beach is evidence that sea level in that location was higher than present. And these raised beaches, you can find evidence of a past connection with the ocean. Often you'll find shells in them that have a marine origin, and they will have a characteristic in the sediments that demonstrates that it was deposited through wave action. One of the places where you can easily see raised beaches is around Hudson Bay in central Canada. And one of the great tools for a geomorphologist or a geologist is Google Earth. So you can actually go and zoom in and look at these for yourself. If you zoom into Hudson Bay, especially around the Manitoba coast, you can clearly see these linear features that stretch for kilometers and can be quite a ways from the modern coastline. If you go on the ground, it's clear to see why these beaches are visible from the satellite imagery in Google Earth. It's because in northern Canada, it's a tundra landscape, so things don't really grow that quickly. So on the surfaces of these raised beaches, there's nothing growing on them. They're gray and lifeless, and they really stick out in the topography. So it's very clear to see that these beaches are there if you go there. There are many ways in which raised beaches can form. There's lots of different geophysical and geological processes that go behind that. The first is that raised beaches existed because in the past, sea level was higher. Global sea level is controlled by the size of ice sheets on the surface of the Earth. Right now, there are ice sheets in Greenland and Antarctica, but in the past, North America and Europe were also covered in ice sheets. And in certain very isolated times in the past 3 million years ago, the Greenland ice sheets and Antarctic ice sheets were actually smaller than they are now. And as a result, the global average sea level was higher. And the last time that happened was in a period known as the last interglacial, which was about 125,000 years ago or so. And at that time, global average sea level was definitely higher than present, because all over the world you find raised beaches and other similar indicators of past high sea level. In 2015, Dutton et al. Came with an estimate that global average sea level was 6 to 9 meters higher than present. But a more recent estimate by Dyer et al. Brought that down to closer to 3 to 5 meters or so. Anyway, the thing is that you will find raised beaches in many places around the world because of the global average sea level being higher than it is now. The second and third reason you'll have raised beaches are related to a process which is known as glacial isostatic adjustment. And this is the bulk of what I research personally. And definitely, I hope in a future episode, I will have a deeper dive into this subject. But for now, the important thing is that in places that were covered by ice sheets and those ice sheets have melted away, the land is slowly coming up because when the ice sheets were there, it pressed down on the earth, and the rocks deep below the surface are kind of really hot, and over long time periods kind of act like a fluid, so it kind of flows away from where the ice sheets were. And after the ice sheets melt away, that those rocks sort of flow back to where that ice loading was. And as a result, after the ice melts away, the land slowly rises and you'll have raised beaches. And that was the example I gave around Hudson Bay. That is the mechanism for that. The second component of glacial isostatic adjustment that causes raised beaches is a process known as ocean siphoning. And this happens further away in what is known as the far field of the ice sheets. So in like tropical areas, for instance. And basically, what happens is because those rocks underneath where the ice sheets were slowly flowing back, that actually causes the land to sink in the areas that were peripheral to those ice sheets. And because that's changing the Earth's shape and the gravitational field, that actually causes water from the equatorial areas to rush towards where the land is sinking. And as a result, in tropical areas, sea level is slowly dropping for the past 5,000 to 7,000 years. And that's, of course, starting to change now, and I will discuss that in the future, I'm sure. Another unrelated reason you'll have raised beaches are due to earthquakes and volcanoes. And this seems kind of obvious. If a big earthquake happens, it can cause the land to go up. And as a result, you'll have a raised beach if that happens along the coastline. A really great example of that is along the coast of Chile on the island of Isla Mocha. And Isla Mocha is a very rapidly uplifting place, and it's estimated there's been about 38 meters of uplift in the past 6,000 years. So if you look on Google Earth and look at this island, you can see a whole bunch of raised beaches there. Volcanoes can also cause raised beaches as the magma chamber inflates. This was actually observed in part by scientists in Italy, and that was reported in Principles of Geology by Charles Lyell, which I'll talk about in a minute. Another reason you might have raised beaches is a process known as dynamic topography. And this is less important for raised beaches in the past 100,000 or 200,000 years, but over longer time periods of millions of years, this is a more important process. So basically what dynamic topography is, the Earth's surface is slowly changing because the rocks deep below the surface are slowly flowing due to convection. So it's kind of like a lava lamp. So basically you'll have the shape of the Earth sort of slowly changing because the rocks are sort of flowing. In general, because of this process and erosional processes, you don't find really ancient raised beaches. But there is a major exception, and that's along the east coast of the United States. So along the Appalachians, there's a very long raised beach, and it's been investigated for at least a century, I think. So yeah, it's been uplifted due to this dynamic topography process. If you go a very long time periods, like the center of North America used to be a shallow sea during the Cretaceous, and now in some places that's been uplifted by over a kilometer. And that's, again, this dynamic topography process. So why would I call the podcast the Raised Beaches Podcast? Well, I studied glacial isostatic adjustment, which is responsible for two of the causes of raised beaches. So, of course, you can use those raised beaches as evidence of what the size of the ice sheets were based on the elevation of the raised beaches, as well as the age and how quickly the succession of raised beaches changes. You can use that information to infer the size of the ice sheets using modeling. So this was a very important component of my PhD thesis, and as a result, raised beaches kind of have a soft spot in my heart, and I still enjoy talking about them and studying them. So because raised beaches to me are so important, I thought, well, when were the first studies on raised beaches? When did that happen? So I went into Google Scholar and I typed in raised beaches and went back to the 1800s, and the first mention of the term raised beaches was found in the 5th edition of Charles Lyell's Principles of Geology, which is one of the fundamental treatises on the discipline of geology when geology was just starting off as a science. However, in Edwards and Craven, they stated that the term was probably first used in Ireland by Irish scientists, and indeed, Lyell was using this term raised beaches when referring to these studies by these Irish scientists. So I went back to these Irish studies, and yes, in the Journal of the Geological Society of Dublin, there were, in 1838, two studies which used the term raised beaches. One was by John Schuler and the other by Joshua Trimmer. Now, the study by Schuler doesn't actually use the term raised beaches within the text. It was just in the title of the journal to describe the paper. However, the second paper by Joshua Trimmer actually goes into detail about what is a raised beach and how it's defined and how it's related to the ocean. So this, to me, is the first true study on a true definition of what is a raised beach. So as I mentioned, the raised beaches were used in Charles Lyell's Principles of Geology as a piece of evidence for his theory on the fact that the Earth is changing. This led to a noteworthy debate because Charles Lyell proposed that the Earth is changing, and some people didn't really agree with him. So this led to a really big controversy back in the 1830s. And this controversy goes back to a scientist named Maria Graham. And Maria Graham, she was an academic and journalist, and she happened to be in Chile during a major subduction thrust earthquake in 1822 called the Valparaiso earthquake. And Graham wrote a very detailed account of the impacts of that earthquake. So because of her very detailed account of this earthquake, it really caught the eye of the geologists in Britain at that time. And they asked her to publish her account in the Journal of the Geological Society. And after 200 years, I think most people probably don't know about this paper, but this paper was quite important for the then nascent discipline of geology. And one thing that was notable about Graham's paper is that it was the first paper published in the Journal of the Geological Society that was written by a woman. And at that time, women were not even allowed to be members of the Geological Society. And I think it really showed that she was very well respected as an academic at that time. So the details of this paper, she basically described that the earthquake caused about over 1 meter of uplift in Valparaiso, and that all along the coast, upwards of 100 miles or 160 kilometers from Valparaiso, there was a substantial amount of uplift. And she noted that the beach was no longer connected to sea level, that there had been the creation of a raised beach. And her quote was, and she actually went further inland and found evidence that there were more raised beaches at higher elevation. And she noted, I found good reason to believe that the coast had been raised by earthquakes at former periods in a similar manner. Several ancient lines of beach, consisting of shingle mixed with shells, extending in a parallel direction to shore to a height of 50 feet above the sea. So this was also proof that over time there had been many similar earthquakes that had uplifted the land. In the first edition of Charles Lyell's Principles of Geology, which was published in 1830, he used this as evidence that the mountain ranges were being created by large earthquakes, and this was one of his major hypotheses, that the world was changing. This was not something that everybody agreed with, and one of the biggest detractors was a geologist named George Bellis Greenough. So Greenough very much disagreed with the idea that the Earth's surface was changing in this kind of manner. So Greenough, he was mostly known as a compiler, and he produced a geological map of England and Wales in 1820, and later on a similar map in British India. In some ways, reading his biography, it feels like he's kind of like an early 19th century version of me, like taking all the data and synthesizing it. But I like to think I'm a bit more open-minded than Greenough was at that time. So in 1834, Greenough was the president of the Geological Society, and he used his presidential address to criticize Lyell's hypothesis. However, he didn't directly attack Lyell. Instead, he attacked the credibility of Graham's account of the uplifted beach, the raised beach that was formed during the 1822 Valparaiso earthquake. And yeah, in a very indirect way, he basically accused Graham of lying. And in one account, he said, oh, she would have been too scared to have been able to write these detailed descriptions. And Graham was not happy about this, and by the time this happened, Graham had remarried, and her name was then Lady Calcott. The account is that she was really angry about this, and her family was also angry, and we're going to challenge Greenough to a duel, and she said, no, don't do that, I can take care of myself. So anyway, her response to Greenough is very cutting and full of snark, and it's so great to read. It's really, you can really tell she does not think much of Greenough. And one of the quotes from this is, Mr. Greenough says further in his address, some mussels and oysters still adhere, she says, to rocks on which they grew. But we know not the nature of these rocks, whether fixed or drifted. Mrs. Calcott was ignorant that there were or might have been drifted rocks until she learned it from Mr. Greenough, for much as she had been at sea, she had never met one. So if you don't know 19th century English, basically, Greenough was saying that these rocks, which were composed of granite, could have drifted onto the raised beach through, the ocean. And Graham basically very sarcastically said she'd never seen a floating rock on the ocean. This response to Greenough was so thorough that the other geologists were like, yeah, Greenough really embarrassed himself by not carefully going over what Maria Graham had wrote in her paper. And Charles Lyell, he became the president of the Geological Society after Greenough's term was finished. So he had his own presidential address and said, well, I had no reason to doubt Maria Graham's observations. And later on, Captain Fitzroy of the Beagle also noted that in 1835, there was a similar earthquake in Chile that also uplifted the land. Later on in that year, he also noted that Charles Darwin had gone back to Valparaiso and confirmed Maria Graham's observations. So Charles Lyell said, I had no reason to ever doubt these observations, and Greenough, whatever. Yeah, that was a really interesting conflict that happened in the early days of geology. Of course, I would be remiss if I didn't talk about my own experiences with raised beaches. And, speaking of the voyage of the Beagle, my story of raised beaches were following in the footsteps of Charles Darwin in Patagonia in Argentina. In 2019, I went on a expedition led by Alessio Rovera, who's now at University of Venice, but at the time he was in University of Bremen. And basically along the coast of Patagonia, there are a series of raised beaches all along the coast. And Charles Darwin was very fascinated by this because he measured the elevation of these beaches and terraces that are along the coast and found each terrace is sort of at the same elevation all along the coastline. And he also noted that the beaches at higher elevations tended to have fewer and fewer fossils that were similar to present-day shells that you find along the coast now. And he also compared the beaches on the Argentinian side versus the Chile side, and noted that these beach deposits are, generally speaking, not deformed or altered like the ones in Chile. And so he noted that there was a difference in the process behind what was creating these raised beaches. So one of the main places that we stopped in our journey in Patagonia and in Argentina was a village called Camarones. Our purpose on this trip was actually just to remeasure some of these raised beach and beach ridge landforms that had been surveyed in the past with less precise measurements. So we were hoping to narrow the range of what we know about past sea level. So in Camarones, the raised beach and beach ridge deposits have been investigated by a PhD student, Carlo Rubio Sandoval, and the preprint of this is out, and hopefully the paper will also be out soon. So that'll be nice summary of what I'm about to say. So in Patagonia, there are several reasons why you have these raised beaches, and Darwin assumed that the land was uplifting because that's what was happening in Chile, and that was very clear that the land was uplifting in Chile. And for some of the really old beaches, that is the case. The land is uplifting not due to earthquakes, but rather due to dynamic topography. And the reason for most most of these raised beaches is actually a few different things. The primary one is ocean siphoning. So basically, the water is getting sucked towards the northern hemisphere due to the rebound of the land after the ice sheets melted away. A second reason is that the continental shelf, like the offshore area of Patagonia, is really shallow, and basically you have the water loading on top of it, and it sort of acts as a lever a bit. So that can also affect the land motion, and that causes that's part of the reason why you have raised beaches there. And finally, you have to remember that in certain times in the past, the ice sheets in Greenland and Antarctica were smaller than present, and that is why some of these raised beaches are preserved as well as they are. So in Camerones, there are 4 raised beaches. The youngest and the lowest, of course, is the Holocene raised beach, which formed between 4,000 and 6,000 years ago, and basically it's these very long wavelengths, very, very gravelly beach ridges, basically. And they indicate that in the past few thousand years, sea level was up to 6 meters higher than it is now. And it's been slowly dropping as a result of this ocean siphoning process. It's very clear to see that these Holocene beaches from the older ones, because there's no vegetation on them yet. The second youngest is deposited in the last interglacial between 115 and 130,000 years ago. All along the coast of Patagonia, you find these raised beach deposits that date to this time period. And what's interesting is you go to these deposits, and some of them are kind of almost like rock now, but you'll find lots of shells in them, and the shells are in really nice shape. They're fully intact. And Carla determined that these deposits indicate that sea level was about 9 meters higher than present, so about 3 meters higher than it was about 6,000 years ago. The third beach ridge is higher than the last interglacial, and it was only preserved in one spot, and it was kind of in rough shape because it was being mined for gravel, and in fact, after 2019, it was completely gone. And but we did get some measurements there, and based on the age that we got from it, we don't know the precise age, but there are 2 possible time windows based on what we know about the history of glaciation in the past 500,000 years. So it either formed between 300 and 340,000 years ago, or between 370 and 420,000 years ago. And this deposit indicates that sea level was about 14 meters higher than present. So again, about 5 meters higher than the last interglacial. So we suspect that this deposit represents the time of the highest global average sea level in the past probably 2 to 3 million years. So it's a really interesting deposit, and it's too bad it's gone now, but what can you do? And finally, the highest elevation beach deposit is much, much older, and it was deposited in the Pliocene, and it was dated by Alessio to be about 5 million years old, and indicated sea level was about 28 meters higher than present. And this deposit probably formed at a time when the Greenland ice sheet was probably not there yet, and the Antarctic ice sheets were smaller than present. And even though this deposit is 5 million years old, you go to it and you just grab it, and it's just like it doesn't seem that old. It's not lithified. You can grab the shell fossils out of it. And yeah, there are not very many places in the world with such a well-preserved beach deposit of that age. So I think the only other place where it is preserved like this is in South Africa. And so it was exciting to see this. It's a very unique deposit. If you go further south of Camerones, yeah, there are older raised beach deposits, and they've been uplifted because of dynamic topography processes. Some of them have been dated to the Miocene, so like 10 to 12 million years old. Anyway, the reason I know some of this is because I wrote a paper on this in 2021. It was fun. I got to compile all the previously published data. So you please check that out if you want to know more information. So in summary, raised beaches were one of the first major pieces of evidence that the surface of the Earth is changing, and provided some nice evidence for some of the early hypotheses of geology. And I use the raised beaches as evidence of past ice sheets, and I use them in my modeling, and I like to compile them, and I've been doing that for a few years now. And of course, raised beaches also continue to be important to know about to determine earthquake hazards. So places that are uplifting due to earthquakes, you can use this information to find out how big past earthquakes were. And of course, we also need to know about past sea level changes to assess future sea level, basically as a baseline. Anyway, that is raised beaches, and in future episodes, the deep dive probably won't be quite this long, but I felt it would be fun to really go into what a raised beach is, because I personally feel a lot of connection to it. So now the deep dive is over, I thought I would go into a more casual discussion on this episode's main topic, which was raised beaches. So if you were watching the video version of this podcast, the example of a beach I gave had this line of gray rocks on the beach, and that picture of the beach was taken in Okinawa. And what those rocks are pumice stones. So pumice is a rock that forms when a volcano erupts underwater. And that pumice is from an undersea eruption that happened in 2021. And the pumice, which can float because it's full of air pockets, reached the Ryukyu island chain, which is in the southernmost part of Japan. And it did impact the economic activities, like it can damage boats, and it can damage habitats for the fisheries, as an example. And if you go, like, I took this picture in Okinawa, but I went to Kikaijima, and it also had a lot of pumice on the shorelines. And of course, in the deep dive, I said, Maria Graham said, "Oh, I have never seen a rock float." And some of the pedantic people would say, "Well, pumice can float." You know, of course, if that was your reaction, I'd say, don't be so pedantic. Like, nobody likes that. And, you know, she wasn't talking about pumice. She was talking about big, heavy rocks that were made of granite. And anyway, the story of Maria Graham is very interesting, and I really suggest reading the paper by Thompson that I linked that discusses this conflict she had with George Greenough. Graham's journey to Chile was actually marked with tragedy because she was going with her husband there, and during the voyage, her husband passed away. So she reached Chile, and she was quite devastated by the death of her husband. And they said, "Oh, we can take you back to Britain right away if you want." And she decided, "No, I'll stay here for a while." Maria Graham, I said she is a scientist, a journalist, and an academic. And in Graham's response to Greenough, she said, "Oh, I'm not really a geologist." And Thompson said she was just being modest. And if you read her account in Chile, like in Chile, her account is like 500 pages typeset. She took a lot of notes. And during that time, Chile was undergoing a civil war. And in many ways, I think it would be more accurate to call her a journalist. But of course, the best journalists are like scientists in the way that they operate. And it's very clear that Maria Graham had a lot of training to be a good journalist and a scientist. And, I can see why she was very upset by George Greenough saying that she would have been scared of the earthquake, because during that time there was a civil war going on in Chile. Like, she clearly could handle everything that went her way. She understood the importance of the careful documentation of what was going on, not just from this earthquake, but also from the civil war that was going on. And anyway, she spent about 9 months in Chile, and afterwards she went back to England because she was invited to become the tutor for the princess of Brazil. So at that time, Brazil was a monarchy. And when she went back, her account of the earthquake was very interesting to the geologists at that time, and that's why they invited her to publish her report. When it comes to the word scientist, it's also important to understand that at that time, the word scientist did not even exist, and it wasn't coined until the 1830s. So, it would be more natural to describe people working at that time as academics, because they were kind of expected to be sort of knowledgeable about a wide range of different topics. And of course, at the time, there was a lot of gender discrimination, and women were not truly able to participate in the same way that men were. And, of course, the Geological Society did not even allow women to be members, but it was very clear that there were women working in fields like geology at that time. Next, one of the figures I used in the main topic was on the uplift of the land after the ice melted away to produce raised beaches. And this is based on a figure in a paper by Farrell and Clark. And this is an important paper because it sort of defined what is known as the sea level equation, sort of the connection between the size of ice sheets and the deformation of land and what sea level is. And this paper is kind of impenetrable to most people because it has a lot of equations in it. But the figure is great, and it really does demonstrate what the impacts of the ice melting has on sea level. But of course, this paper was written in the 70s, and the figure itself is very grainy, and it was from a scan from this old paper. So I redrew it myself. And it was a very important paper, though. A lot of the work that I mentioned during the topic was by Alessio Rovera, and we first met in 2018, I believe, and I was working at the Alfred Wegener Institute in Germany, and he was a professor at University of Bremen. And if you don't know the geography of Germany, it was only a 30-minute train ride away. So it was very easy to introduce myself, and we came up with a project to work on paleo sea level and ice sheet reconstructions. And Alessio has been a big influence in the paleo sea level community in the past 15 years or so, and he's done a lot of work on. He did a lot of work on this Pliocene raised beach in the eastern United States, and also we went to Argentina. He spearheaded this large database of last interglacial shorelines called WALLACE, the World Atlas of Last Interglacial Shorelines. And I contributed to 2 papers for this database, including the Argentina one. And I was very happy to have had the opportunity to go with him to Argentina, and I learned so much, and I really appreciate all that Alessio has taught me about the geological end of raised beaches and other shoreline features that indicate past sea level. And of course, last interglacial, I'm sure I'll have a deep dive on that at some point. And the last interglacial was a period where globally temperatures were higher than present, or well, maybe not present, but before the rise in carbon dioxide, 100 years ago. And sea level was definitely higher than it is now. But it is complicated because, as I said, the sea level changes in time and space. So in order to determine what the past sea level was on a global average, you need to consider the configuration of the ice sheets and how they melted and how they regrew afterwards. And this kind of, we don't have a lot of evidence of what this past sea level was between about 120 and 20,000 years ago. So it's difficult to know the precise history of what the ice sheets were doing in order to make a nice model of what the ice sheets looked like during the last interglacial. And yeah, I do hope to tackle this problem in the future if I get the opportunity. We'll see how it goes. I gave an example of raised beaches in the Hudson Bay area, and this picture was from the work of Isabelle McMartin. And Isabelle has been a very prominent glacial geologist who's done a large volume of work on the glacial history in the area west of Hudson Bay. And I have a great deal of respect for her work on this topic. And it can't be easy to do work in this very remote area. It's one of the most remote areas in North America. There's only a couple of villages up there. So to do the field work, you need to have there's a lot of logistical difficulties. And finally, I wanted to say my trip to Argentina was quite a whirlwind. So when I did the trip, I started in Japan, actually. I'm currently in Japan. I had tickets to the Rugby World Cup, which happened in October 2019. But I had to be in Argentina at the end of October 2019. So I flew from Japan to Germany, and then from Germany to Argentina. And that's almost literally the opposite end of the world from Japan. And yeah, it really, I really hope I don't have to do a trip like that again. But it was definitely worth it. And Patagonia is really a desert area. So all that's there is some shrubs and grasses and sheep, lots of sheep. And the native animals, they're these guanacos, and they kind of look like a llama. They're bit different, but kind of look like that. And there are these little birds called rhea. They're kind of similar to a mini emu. They're ratite, and so those animals were everywhere. One very notable thing in Patagonia is that everything is covered in these little rocks. They're maybe 1 to 2 centimeters wide, and the rocks are everywhere, and you're like, there are no hills, there are no outcrops of rock. Where did these rocks come from? And Charles Darwin, in his 1846 papers on Patagonia, he also was like, why are these rocks everywhere? And he called it the Great Patagonian Shingle. And yeah, even now it's not really clear where these rocks come from and why they are there. The leading hypothesis is that due to the rise of the Andes and the general global cooling in the past 5 million years, an ice sheet formed over the southern Andes called the Patagonian ice sheet. And basically the ice sheet grew, and that eroded the rocks off of the Andes Mountains. And due to the meltwater flowing off of the ice sheet, that distributed these little rocks everywhere. And the rocks have been sort of polished off because of wind action. It is incredibly windy in Patagonia. There were dust storms when we were there. Before I finish off on this topic, I should mention that the trip to Argentina that I made was part of a European Research Council funded project called Warm Coast. And Warm Coast was led by Alessio Rovera, and the goal of this was to investigate last interglacial sea level around the world. And the World Atlas of Last Interglacial Shorelines was also part of that. So that's it for Raised Beaches. I hope you enjoyed it. One of the goals I have for the Raised Beaches podcast is to introduce scientific papers that I personally find interesting. And they'll always have a paleoclimate focus, but maybe they'll be biased to the things that I research. Today, I'm only going to introduce one paper because this podcast is already running quite long. And this paper is based on a presentation that I saw at the Japan Geoscience Union conference that I was talking about earlier. And it's by Sun-Ming Hu and et al. And its title is Sustained North Atlantic Warming Drove Anomalously Intense MIS 11C Interglacial. And this was published recently in Nature Communications. So the first question you probably have is, what is MIS 11C? If you are into paleoclimate, MIS is of something that you'll become very familiar with, and it stands for Marine Isotope Stage. So in paleoclimate, we divide time periods into these so-called isotope stages, and they're derived from oxygen isotope variations in the oceans, which are measured from these single-celled organisms called foraminifera. And I'll do a more detailed discussion of this in a future episode. But the important thing is that there are two major isotopes of oxygen. One has oxygen 18, which has 10 neutrons, and oxygen 16, which has 8 neutrons. And because oxygen 18 is slightly heavier than oxygen 16, when there's evaporation coming out of the ocean, oxygen 16 will preferentially be taken out. And when the ice sheet builds up, that means in the ocean, oxygen 18 will increase. Marine Isotope Stage 11C is a period between 396 and 426,000 years ago. there's been measurements of these oxygen isotopes since the Pliocene, about 5 million years ago. And basically, there's these rhythmic changes in the oxygen 18 to oxygen 16 ratio. So this corresponds to times when the ice sheets expanded and shrank in the northern hemisphere. So what's special about Marine Isotope Stage 11C is that it is the longest and most intense interglacial in the past 3 million years during the Quaternary. However, the issue is that the changes in these oxygen isotopes, the buildup and the shrinking of the ice sheets, follow what is known as Milankovitch orbital theory. And in essence, what that is that because of the gravitational attraction of the planets, the Earth's axis of rotation will slowly change relative to the plane of the Earth's orbit. And during the times when the Earth's axis of rotation is pointed towards the sun in a more direct way during the northern hemisphere summer, you'll have what is known as an interglacial period where the ice sheets will shrink. And when it's pointed away, the ice sheets will grow. So Marine Isotope Stage 11 doesn't follow that so well because the intensity of the northern hemisphere summers during this period was not particularly large compared to other interglacials, including the Holocene, the current interglacial. So with that context, Hu et al. Measured a climate record from a rock known as a flowstone. So a flowstone is a type of speleothem, a cave rock. So in a cave, you'll have water dripping down from the top of the cave, and the water will contain a certain amount of calcium, and that calcium will precipitate out of the water and form a mineral called calcite. And over time, these rocks, like a flowstone, will slowly grow. And basically what you can do is you can take a slice or a drill through the flowstone, and you measure the chemistry of the rock over time, and that gives you an understanding of the conditions of the water. And the water chemistry will change based on what the climate is. So, for instance, if you have warmer temperatures or precipitation sources changing, or if it's drier, or if it's wetter. So these things affect the chemistry of the water that's dripping down to form these flowstones. So this flowstone record comes from a cave in northern Italy called the Basura Cave, and the chemistry in the flowstone should reflect changes to the climate in the northeastern Atlantic and the Mediterranean. And their hope is to link this record to marine isotope records, which stretch for a much longer period of time. And the marine isotope records are not very well defined in terms of chronology, but with a speleothem, in this case a flowstone, it's possible to get a really precise age on the chemistry record, because you can use uranium-thorium dating. So uranium gets incorporated into the calcite of the flowstone, and uranium, it's radioactive, so over time it converts to thorium, and based on the amount of thorium relative to uranium, you can tell what the age is. And this is what they did. They collected a lot of uranium-thorium dates to find the precise age of the flowstone record. There was a few things that they measured. The first is the strontium and calcium ratio. And carbon isotopes, so the ratio of the carbon isotope 13 and the carbon isotope 12. And these records give an indication of how dry and cold it is above the cave. So when the relative amount of strontium increases and when the relative amount of carbon-13 increases, this tells you that the conditions were colder and drier. And conversely, if the strontium decreases and the amount of carbon-13 decreases, that's an indication that it's wetter. And this cave record, or this flowstone record, really does show that. It shows that during the MIS 12 glacial period, conditions were drier and colder, and during the MIS 11 C interglacial, it was warmer and wetter. And in fact, there was a hiatus on this flowstone record in the middle of the MIS 12 glaciation. And that's probably an indication that there wasn't water dripping in this cave, possibly because there wasn't enough rainfall, or maybe the top of the cave was frozen because it was so cold. During the interglacial, this strontium, calcium, and carbon isotope record indicates that there was kind of a two-peak signature in the MIS 11C interglacial. One was between 418 and 424,000 years ago, and the other was between 402 and 412,000 years ago. And if you look at the insolation, the orbital theory, it kind of matches that signal. So it seems that in northern Italy, the climate was responding to the changes in the northern hemisphere summer due to the Milankovitch orbital theory. The other thing that they measured was oxygen isotopes, so the relative amount of oxygen 18 to oxygen 16. And of course, if the amount of oxygen 18 increases, it should be an indication that there's a glacial period. But this record, it's kind of not diagnostic of a specific climate signal. And as a result, they didn't really interpret it in terms of climate changes. The main thing of interest with this record is to precisely date the end of the MIS 12 glaciation and the start of the MIS 11C interglaciation. This has been defined before using these oxygen isotope records from the ocean, but the chronology of the marine isotope records generally have been tuned to this Milankovitch orbital theory. And like I said, the Milankovitch orbital theory doesn't really work well with this MIS 11C interglacial. So that means there's a big uncertainty on the chronology of when the transition from the glacial to the interglacial period happened. So they did some statistical methods, and they were able to align this flowstone record with the marine records, and they were able to pinpoint the timing of the start of the interglacial to be about 426,000 years ago. At the end of the paper, they then go into some speculation about the overall climate situation during Marine Isotope Stage 11. And one of the puzzling things that many scientists wonder about is that, because of this contradiction to Milankovitch theory, you look at the sea level reconstructions. And again, these sea level reconstructions are based on these marine isotope records. It seems to suggest that once the interglacial started, the sea level was still quite low compared to present. And basically, it took about 15,000 years for the sea level to get close to the present day sea level. And at its peak, they think that sea level was, quite a bit higher than present during this interglacial because it's so long lived. And their speculation is that because the northern Atlantic region was quite warm and for a very long period of time, that this might have been why the ice sheets were able to retreat, even though the summer intensity was not particularly high. Anyway, for me personally, I said this as a comment in the WHO's presentation that I think there should be more caution to interpret this sea level record because, as I said, this sea level reconstruction is based on these marine isotope records, and the chronology is based on the assumption that Milankovitch theory is what's driving the growth and retreat of the ice sheets. And yeah, that doesn't work in Marine Isotope Stage 11C. So the uncertainty on this reconstruction is going to be quite large. In my opinion, the collapse of the ice sheets probably happened much earlier than what the sea level reconstruction says. And there's some other evidence which I might talk about when I do a deep dive into Marine Isotope Stage 11C in a future episode. But yeah, this is a very important climatic record, and I was very interested in reading it. So anyway, that is the end of episode 1 of the Raised Beaches podcast. Please tune in next time where the deep dive will be a deep dive into what is sea level. So see you then. Thank you for listening to the Raised Beaches podcast. If you enjoyed this, please follow my social media accounts where I post more information on the paleoclimate sciences. I am on Mastodon with the username @DrEvanGowan@FettyScience.org. On Bluesky, my username is @evangowan.bsky.social. On LinkedIn, my username is Evan James Gowan. I hope you tune in next time. Thank you.